42 hours ago, Comet 31P/Schwassmann-Wachmann erupted with an outburst so violent it doubled in brightness in under 6 minutes, while ground-based observers scrambled to capture what NASA's own models said should be impossible at this distance from the Sun. Official explanations point to subsurface ice pockets and thermal stress. But the photometric data tells a different story. Synchronized brightness spikes across multiple wavelengths, a debris field expanding at speeds that defy conventional outgassing, and a rotation period that shifted by 47 seconds in a single night. If what triggered this event is truly natural, we need to rewrite the physics of how comets behave in the outer solar system. And the next outburst could happen at any moment. On February 8, 2026, the Lowell Observatory's 4.3-meter Discovery Channel telescope locked onto 31P/Schwassmann-Wachmann during a routine monitoring session. The comet sat at 5.9 astronomical units from the Sun, well beyond Mars, in a region where solar heating should be negligible. At that distance, water ice remains lock solid. Outbursts, when they happen at all, are supposed to be gentle affairs, gradual brightenings over days or weeks as subsurface pockets slowly warm and release pressure. What happened instead rewrote the observing schedule for a dozen facilities worldwide. At 3:14 Universal Time Coordinated, the comet's integrated magnitude stood at 14.2, consistent with its baseline brightness for the past 3 weeks. By 3:20 Universal Time Coordinated, just 6 minutes later, it had surged to magnitude 13.1. That is not a gradual release. That is a detonation. The brightness increase represents more than a doubling of the light output in the time it takes to brew coffee. Follow-up observations from a Nordic optical telescope and the Gemini North facility confirmed the spike and revealed something even stranger. The outburst was not fading. It plateaued, holding steady for nearly 11 hours before beginning a slow decline. This is not the first time 31P has thrown an outburst. The comet is famous for them. Since its discovery in 1927, it has erupted dozens of times, earning a reputation as one of the solar system's most unpredictable objects. But this event is different. The speed, the intensity, and the wavelength signatures do not match the historical pattern. As observatories worldwide pivoted their instruments toward this icy enigma, the data began piling up, and with it, a growing list of contradictions that standard comet models cannot resolve. While professional observatories coordinated their response, the first alarm did not come from a multi-million-dollar facility. It came from an amateur astronomer in rural New Mexico. Daniel Kurtz, operating a 14-inch Schmidt-Cassegrain equipped with an SPIG CCD camera, caught the initial brightness surge during a time series photometry session he had been running for a citizen science project. His images, plate solve against the UCAC for catalog and log with GPS-synchronized timestamps, showed a magnitude jump in brutal clarity. Within 90 minutes, Kurtz had uploaded his calibrated FITS files to the Comet Observation Database and flagged the event on the amateur astronomy forums. By dawn, observers in Europe and Asia had confirmed the outburst and begun their own monitoring campaigns. What followed was a masterclass in distributed astronomy. Amateurs across 4 continents coordinated observations, staggering their sessions to provide near-continuous coverage as 31P rotated through its 57-hour period. The data quality rivaled professional work. Images were dark subtracted, flat-fielded, and calibrated against Gaia DAR 3 astrometry. Photometric measurements included error bars and extinction corrections. One observer in southern France, using a backyard 16-inch Dobsonian and a high-speed CMOS camera, captured time-resolved brightness variations at 10-second cadence, something no single professional observatory had attempted. That dataset would later prove critical. This flood of community-sourced observations did more than supplement the official record. It exposed details that might have been missed entirely. While large telescopes focus on spectroscopy and broadband imaging, the amateurs were catching transient features, short-lived brightness flickers, and asymmetries in the expanding coma that appeared and vanished within minutes. The global network was not just watching. It was documenting an event in real time with a temporal resolution that even billion-dollar space missions struggle to match. An outburst at 5.9 astronomical units should not pack this kind of punch. At that distance, The sun's energy is spread thin, delivering just 2.8% of the intensity Earth receives. Water ice, the usual suspect behind comet activity, stays frozen solid, for subsurface pockets to explode with enough force to double the comet's brightness in 6 minutes. The energy budget has to come from somewhere else. One possibility is carbon monoxide ice. CO sublimates at much lower temperatures than water, and even at 31P's frigid distance, pockets of CO could theoretically build pressure beneath an insulating crust. When the crust fails, the release is sudden and violent. The problem is the math. To generate the observed brightness increase, the outburst would need to eject roughly 800,000 metric tons of material in those first 6 minutes. That is not a leak. That is a catastrophic rupture. Dr. Naomi Saito, a planetary volatile specialist at Kyoto University, ran the thermal models. She points out that even with generous assumptions about CO content and subsurface temperature gradients, the required energy release is extreme. You would need a CO reservoir several meters deep, spanning at least 200 meters across the surface, all venting through a relatively small fracture, she explains. The pressure buildup alone would imply structural stresses that should have triggered smaller precursor events. We saw none. The gas velocity adds another wrinkle. Spectroscopic observations from the Keck Observatory measured outflow speeds, peaking at 1.2 kilometers per second during the initial surge. That is 3 times faster than typical comet gas jets. CO sublimation can reach those speeds, but sustaining them for 11 hours requires a continuous supply of material far larger than what the surface area of 31P should reasonably contain. The comet's nucleus is estimated at roughly 4 kilometers across. Losing 800,000 tons in 6 minutes, then maintaining elevated activity for half a day, means the object shed at least 0.5% of its total mass in a single event. Comets do lose mass. That is what they do. But shedding 0.5% in one go from an object that spends most of its time in the cold outer solar system pushes the boundaries of what volatile-driven activity can achieve. The number's close only if the subsurface is a ticking time bomb, packed with unstable ices waiting for the slightest trigger. And if that is true, 31P should be fragmenting or visibly altering its structure with every major outburst. Yet, orbit after orbit, it remains intact. The physics is uncomfortable. The energy is there in the light curve, undeniable and measured. But the source, the mechanism that could deliver this much violence at this distance, keeps slipping through the cracks of every conventional model. For decades, 31P has followed a predictable rhythm. Outbursts come and go, brightness flares, the coma expands, and within days or weeks, the comet settles back to baseline. The rotation period, measured repeatedly since the 1990s, has held steady at approximately 57.5 hours. It is a slow, lumbering spin, typical for a mid-sized comet nucleus shaped more like a lumpy potato than a smooth sphere. That stability ended on February 9th. Photometric monitoring by the 10.4-meter Grand Telescopio Canarius revealed something no one anticipated. The light curve, which should have maintained its familiar 57.5-hour cadence, was off. The periodicity had shifted. By the night of February 10th, multiple independent observers confirmed the change. The new rotation period clocked in at 57 hours and 13 minutes, a decrease of 47 seconds. That might sound trivial. It is not. Changing a comet's rotation rate requires torque, and torque requires force distributed unevenly across the nucleus. In the standard model, outgassing provides that force. Jets erupting from active regions on the sunlit side can act like tiny rocket engines, nudging the nucleus into a faster or slower spin, depending on their orientation. The effect is well documented. Comet 67P/Churyumov-Gerasimenko, studied up close by the Rosetta spacecraft, showed measurable spin-up as gas jets fired asymmetrically from its surface. But 31P is different. The magnitude of the spin change is larger than what the observed outburst should produce. Dr. Michael Belton, a comet dynamics researcher who has spent years modeling rotation changes in active comets, ran the numbers. To shift a 4-kilometer nucleus by 47 seconds in a single event, the outgassing jets would need to sustain a net torque of roughly 3 times 10 to the power of 12 Newton meters over the 11-hour plateau phase. That is achievable, but only if the jets are highly asymmetric and aligned almost perfectly to maximize rotational leverage. The problem is the geometry. High-resolution images from the Hubble Space Telescope, captured 18 hours after the outburst, show the expanding coma as nearly spherical. There is no clear evidence of concentrated jets or active regions dominating one hemisphere. The debris field looks isotropic, as if the material erupted from multiple points across the surface rather than from a single localized vent. If the outgassing was that evenly distributed, it should not have spun the nucleus up at all. There is another possibility, one that physicists quietly acknowledge but rarely explore in print. If the mass loss itself was uneven, if one side of the nucleus shed significantly more material than the other, the resulting recoil could impart the necessary torque. But that introduces a new question. What would cause such a lopsided eruption? Subsurface reservoirs do not choose sides. They respond to heat and pressure, and at 5.9 astronomical units, both should be evenly distributed across a slowly rotating body. The rotation change is not just an oddity. It is a data point that does not fit the narrative. And when the spin period of a comet shifts in lockstep with an outburst that itself defies the energy budget, the models start to crack. The question is not just how 31P erupted, it is what mechanism could simultaneously trigger a violent outburst and impart a measurable rotational acceleration without leaving an obvious asymmetric signature in the debris field. The outburst may have been dramatic, but the real puzzle emerged in the spectroscopic data. When light from 31P passed through the spectrographic Keck and the Very Large Telescope, the emission lines did not just reveal what gases were present. They revealed when those gases appeared and in what sequence. That timing, down to the minute, does not match what a purely volatile-driven event should produce. In a typical comet outburst, water vapor dominates the early phase. As subsurface ice heats and vents, H2O emission spikes first, followed by secondary species like CN, C2, and CO as the expanding coma breaks down under solar UV. The sequence is well understood and has been observed in dozens of comets. For 31P, the timeline ran backward. At 3:17 Universal Time Coordinated, just 3 minutes into brightening event, spectra from the Nordic Optical Telescope showed strong CO emission lines with only faint traces of water. By 3:45 Universal Time Coordinated, CN and C2 had surged into prominence, while H2O remained surprisingly weak. It was not until nearly 2 hours after the initial spike that water vapor emission caught up and began to dominate the spectrum. The reversal is difficult to reconcile with standard sublimation physics. Water ice and CO ice do not choose an order. They respond to temperature. If heat is driving the outburst, the most volatile species should vent first, but the most abundant species, water, should follow almost immediately as the surface warms. Instead, 31P seemed to erupt in stages, with each chemical signature appearing on a distinct schedule. Dr. Elena Vidal, a cometary spectroscopist at the European Southern Observatory, has been analyzing the VLT data. She notes that the delayed water emission could be explained that the initial outburst excavated deep subsurface layers rich in CO and carbonaceous compounds, with water ice unexposed later as the debris field expanded. But that requires a very specific stratigraphy, she explains. You would need meter-thick layers of CO-rich material capped by a water-poor crust, all arranged in a way that the explosion peels them back in sequence. It is possible, but it is not what we typically see. There is another anomaly buried in the timing. The emission lines did not just appear in sequence. They pulsed. High cadence spectra from the 10-meter Keck 2 telescope, captured every 90 seconds during the plateau phase, revealed periodic intensity variations in the CN emission. The brightness of the CN line peaked and dipped with a regular cadence of roughly 11 minutes. Water vapor showed a similar but weaker modulation. CO emission remained steady. Periodic variations in emission lines are not unheard of. Rotating nuclei with localized active regions can produce brightness fluctuations as vents rotate in and out of view. But 31P's 57-hour rotation period is far too slow to explain an 11-minute cycle. The only way to generate such rapid modulation is through something happening in the coma itself. Perhaps clumps of material tumbling to the field of view, or localized pockets of gas interacting with solar radiation in bursts. Neither explanation is particularly satisfying, and both raise more questions than they answer. The spectroscopic timeline is not just unexpected. It is a signature that standard outgassing models do not predict. The sequence, the pulsing, and the delayed water emission point to a release mechanism that is either far more complex than a simple rupture of subsurface ice, or driven by processes that have not yet been seriously considered. And as the data accumulates, the gap between observation and theory continues to widen. For months, Dr. Abby Loeb's research group at Harvard has been assembling a detailed analysis of 31P's February outburst. Their manuscript outlines the energy contradictions, the rotation anomaly, the spectroscopic sequence, and a hypothesis that the event may have been triggered by a subsurface structural failure rather than purely thermal processes. The implications are narrow and testable. If the outburst was mechanical, future events should follow similar
Here
patterns,
are 22
with
video
rapid
generation
onset,
prompts.
multi-stage emission, and measurable spin changes. The paper is rigorous, the data is public, and the conclusions are framed as an invitation for further observation and modeling. The manuscript was submitted to the Astrophysical Journal in late February. It was declined within 72 hours, without being sent to peer review. The editor's response cited concerns about speculative mechanisms, and noted that the hypothesis, while mathematically sound, strayed too far from established volatile sublimation models. A second submission to Icarus met a similar fate. This time, the rejection letter included a single line suggesting the work might be better suited for a more exploratory venue, a polite dismissal that avoided engaging with the data itself. This is not an isolated case. Loeb's earlier work on interstellar objects and non-standard comet behavior has faced repeated resistance from traditional journals, even when the observations are uncontested and the models aren't testable. The pattern is familiar. When a hypothesis challenges deeply held assumptions, especially assumptions about what comets are and how they must behave, the response is often not critique, but gatekeeping. The data are not refuted. They are simply ignored. Dr. Naomi Saito, whose thermal models were cited in the manuscript, has expressed frustration with the process. The energy budget does not close.
Coordination.
The rotation change is real. The spectroscopy is published and verified by multiple facilities. These are not speculative claims. They are observations that need an explanation. She points out that the role of peer review is not to protect consensus, but to test ideas against evidence. When journals decline to circulate work that meets basic standards of rigor, the conversation stalls, and the anomalies remain unaddressed. The cost of this gatekeeping is not just academic. It shapes which questions astronomers feel safe pursuing and which observations get funding and telescope time. If the data from 31P suggests something beyond a standard sublimation model, the scientific process should encourage exploration, not silence. Instead, the manuscript sits unpublished. The evidence remains in preprint archives, and the broader community is left to wonder why an outburst that broke the rules is not generating the debate it deserves. For Loeb and his collaborators, the frustration is sharpened by the knowledge that 31P is not done. The comet is still active, still monitored, and still capable of throwing another outburst at any time. If the next event follows the same pattern,
here are 22 video generation
gains
prompts.
weight. If it does not, the model can be refined or discarded. That is how science is supposed to work. But only if the work is allowed into the conversation. On April 3rd, 2026,
Global coordination.
31P will reach aphelion, the farthest point in its 14.9-year orbit, at a distance of roughly 6.7 astronomical units from the Sun. At that distance, solar heating will be at its weakest. According to every conventional model, the comet should be dormant, locked in a deep freeze with no thermal energy to drive further outbursts. If the February event was purely the result of subsurface CO pockets venting under solar influence, aphelion should mark the end of activity until the comet begins its slow journey back toward the inner solar system. But what if it does not go quiet? What if, against all expectation, 31P erupt again while parked at the cold edge of its orbit? That single data point would shatter the thermal model and force a reckoning with alternative mechanisms. Observatories worldwide are preparing for that possibility. The European Space Agency's Gaia spacecraft, which has been passively monitoring 31P's position and brightness as part of its all-sky survey, has flagged the comet for increased observation cadence through May. Ground-based facilities, including the Lowell Observatory and the Pan-STARRS Survey telescopes, have allocated time for monitoring campaigns. Amateur networks are mobilizing as well. The same global collaboration that captured the February outburst in real time has committed to round-the-clock photometry and astrometry through aphelion and beyond. Observers are coordinating schedules, sharing calibration templates, and preparing data pipelines to ensure that if 31P brightens, even slightly, the event will be documented within minutes. The templates are detailed. FITS headers with WCS tied to Gaia DR3, UTC synchronized timestamps, filter specifications, and standardized magnitude calibration. Every observation will be submitted to the Minor Planet Center and cross-checked against multiple independent datasets. The stakes are clear. If 31P erupts at aphelion, the implications reach beyond a single comet. It would mean that outbursts in the outer solar system can be driven by mechanisms unrelated to solar heating, mechanisms that can include structural instability, radiogenic heating from long-lived isotopes, or stored energy from previous perihelion passages. Each possibility opens a new branch of research and demands new models that current theory does not accommodate. Dr. Michael Belton, who has been modeling the rotation anomaly, puts it plainly: aphelion is a test. If we see activity, we are no longer talking about sublimation physics. We are talking about something endogenous, something internal to the comet that does not depend on the sun's input. That changes everything. The observation window is narrow at aphelion. 31P will be faint, likely hovering near magnitude 16 or dimmer, testing the limits of all but the largest amateur telescopes. Professional facilities will have the advantage, but amateurs will provide the continuous coverage that no single observatory can match. The global network is ready. The data pipelines are tested, and the world's eyes, professional and amateur alike, are fixed on a dim speck of ice and rock at the edge of the solar system, waiting to see if it breaks the rules one more time. Right now, a comet in the outer solar system is rewriting the textbook on what volatile bodies can do, one that official models quietly set aside, even as independent observers capture evidence that refuses to fit the script. As 31P drifts toward aphelion, the line between understood physics and unexplained behavior grows thinner. What we choose to investigate today shapes what we understand tomorrow. Curiosity is not reckless. It is how science moves forward. What do you make of it? Let us talk in the comments.